Hey guys, this is Group 6 paper presentation by I'm Nikhil Lalkota and my teammate is Robert Smith. Today we are going to talk about Morpheus towards automated SLOs for enterprise clusters. And this paper is written by few people from Carnegie Mellon University, University of Illinois, University of Fribourg and Technion Israel Institute of Technology. So let's get started. The introduction to Morpheus. Analysis of large-scale production cluster workloads reveals large variance in job runtimes. User surveys suggest that this variance is perceived by users as unpredictability. So the users are unable to predict how much resources are needed for a particular job, and most of the time they end up provisioning much more resources than the required resources. So this Morpheus system attempts to observe all the historical data and infer SLOs, schedule tasks to reduce SLO violations in a predictable manner, and it also handles unpredictability via dynamic reprovisioning of cluster resources. It is believed that Morpheus lowers cluster footprint by 14 to 28%. So let's talk about the problems mentioned in this paper. So modern frameworks for large-scale analytics doesn't solve the problem between high cluster utilization and job performance predictability. And the second problem is, for the cluster users to ensure predictable performance, they are forced to over-provision resources, which leads to poor cluster utilization and wasted computational resources. And the third problem mentioned is divergent predictability and utilization requirements are poorly handled by current existing systems. So what are the motivations? The vast majority of cluster jobs are production jobs. As you can see in the pie chart here, 75% of the jobs are production jobs and 15% of them are ad hoc, and the rest 10% are the failures of job. So it clearly shows that greater than 60% of production jobs are periodic, typically occurring in 1 hour or 1 day intervals. This suggests that Morpheus should focus efforts on optimizing scheduling for recurring production tasks rather than ad hoc tasks. So based on this, the authors have analyzed execution logs of millions of jobs running on clusters with more than 50,000 nodes. And they have also interviewed a lot of users, and they have done analysis of discussion threads, escalation tickets, which helped in understanding one important thing the users really care about, which is job completion by deadline. So, and the other motivations discussed are infrastructure deployment or upgrade logs, selection of targeted micro benchmarks, and the rest we'll talk in the next slide. User surveys. As we have seen in the previous slide, the majority of the jobs are production jobs, and user care most about these production jobs which run regularly. So 90% of escalations are related to production tasks. Users typically prefer a job scheduler that is predictable even if there are any sacrifices in fairness or any other aspect. The users are 120% more likely to complain about unpredictability in job completion time than about scheduling fairness. So, based on these facts, like Morpheus, the authors are convinced that Morpheus should focus on meeting the user's expectations and requirements for job completion, especially for production jobs when compared to ad hoc tasks. Predictability challenges. Manual tuning of jobs is hard. It is very difficult to avoid provisioning of excessive resources. 75% of manually provisioned jobs are over provisioned, and it is also very difficult to predict how long a certain task will take time to complete. And normal performance can be modeled. Outlier performance requires a dynamic approach that can adapt to deviations from the mean. Ma- Changing conditions. Runtime of jobs can be difficult to predict due to changes in cluster hardware. As you can see in this diagram, 40% of difference in runtime between server SKU1 and SKU2. User scripts always keep changing. Within 1 month, 15 to 20% of jobs had major changes, and the other month you see there are no changes at all. So this makes it difficult to predict the runtime and the amount of resources that particular job required. So what are the key ideas discussed? The first one is automatically deriving SLOs and job resource models from historical data. And the other one, relying on recurrent reservations and packaging algorithms to enforce SLOs. The last is dynamic reprovisioning to mitigate inherent execution variance. We'll discuss one by one in the next slide. Morpheus key components. Given a job that is periodically submitted by a user, Morpheus quietly monitors the job over time and captures a provenance graph with data dependencies and ingress or egress operations. Telemetry history in the form of resource guidelines capturing resource utilization following a number of successful runs of the job. An SLO inference component performs an offline analysis. Using the provenance graph, it determines a deadline for completion, the service level objective, and using the skylines, it determines a model of the job resource demand over time. At this point, the system is ready to take over resource provisioning for the job. But before it does so, Morpheus then uses recurring reservations for each managed job. These set aside resources over time for running the job based on the job resource model. Let's discuss about each component. Provenance graph to capture inter-job data dependencies. SLO extractor use PG to statically derive deadline. Job resource model take history to create tight envelope R, and then user sign off or override, and online packaging algorithm for reservation placement, and then monitoring job progress and automatically adjust the resource based on the results. Morpheus goals: eliminating sharing induced unpredictability to enforce SLOs while retaining high utilization in a shared environment, and this consists of controlling performance variance with minimal resource over-provisioning. Mitigating inherent unpredictability, dealing with inherent performance variance. So the main goal is to determine the to mitigate the unpredictability of the jobs and dynamically allocate the correct amount of resources required for a particular job at a particular time. Experimental validation. In this design, by implementing Morpheus atop of Hadoop or Yarn, perform several simulations on production cluster with over 50k nodes, which shows that SLOs derived are representative of the job's needs. What are the limitations of Morpheus? First one is control over globally shared resources. It relies mostly on the resource management infrastructure to enforce its decisions. Morpheus can only enforce container-level resources, such as CPU or memory, but lacks control over globally shared resources, like DNS server. Support of non-periodic jobs. Morpheus does not automate the SLO and job resource model extraction for never-seen-before jobs, and it has slightly disadvantage with the ad hoc functionality as it mainly focuses on periodic jobs. Automatic SLAs. It does not aim at delivering full-fledged automated service level agreements, which includes a specification of the business aspects of the provider-user agreement. SLO inference. The goal of the Morpheus is to crystallize what users perceive as good enough job performance through automatically generated targeted SLO. Morpheus can handle load in production clusters. It provides more accurate resource estimates, level of fitting controllable in the inference modules of Morpheus, predictable performance with lesser resources and higher utilization. Provenance graph. Reasoning about clustered data. It gathers logs capturing key aspects of job execution, file system accesses, and system metrics and represent them graphically. Node represent jobs and files in our clusters, and edges capture read or write operation among jobs. And the next slide will be explained by my teammate Robert. And yeah, thank you.
Morpheus creates a job resource model, which is a high-fidelity model of the resource requirements of a particular periodic job. Morpheus analyzes past period job data and solves an LP problem to fit the model to the data. A parameter alpha is available to the user to adjust how much the model will overallocate resources. It's important to note that the authors assumed that the minimum parallelism of a job is a single container, but this assumption can be manually overridden by the user if they have additional knowledge of the jobs. Automatically determining the minimum parallelism of a job is left as a potential improvement to Morpheus that could be made in the future. Morpheus packs jobs efficiently by using a cost-based algorithm called low cost. The idea behind the low cost algorithm is to allocate each job in such a way that it's efficient with respect to the cost. And the cost in this case represents the current load of the cluster. There's an inherent inefficiency that's associated with calculating and storing a separate reservation for each instance when these jobs are periodic. After all, periodic job may repeat many, many times. To address this, a constraint was issued that all instances of the same periodic job would have the same offset with respect to the period. This design gives up some flexibility in scheduling, but it's much more predictable for operators, and it's also simpler to implement in the algorithm. And here's an example of the low-cost algorithm in action. As you can see in the graph, the algorithm looks at the number of containers that are required for the current provisioning. That's the demand. And it performs some simple arithmetic. It uses that to determine where the containers for that job should be allocated around the other jobs that are already placed to most efficiently use the available resources. The low-cost job placement algorithm has a couple concrete goals. The first goal is to allocate containers for all periodic jobs such that all the requirements can be met within the deadline allocated for that job. The second goal is to try to minimize the amount of time that you'd have to wait before an ad hoc job would begin when you don't know when these jobs are going to actually show up. So when packing with the low-cost algorithm, it uses a cost-based approach that tries to allocate all of these jobs while taking into account the current load on the cluster, along with what the demand is for that particular job. When trying to balance between non-periodic jobs and periodic jobs, Morpheus always assumes that periodic jobs have priority. And this is based off of the analysis that was done earlier, where it was seen that the vast majority of production jobs are periodic in nature. Because Morpheus always considers periodic jobs to be business critical production jobs, they always have a higher priority than the non-periodic jobs. So whenever it needs to allocate resources for a new periodic job, non-periodic ones may get bumped, right? They may lose their resources in favor of the periodic job, which has higher priority. When Morpheus is scheduling those non-periodic jobs, though, it uses the same algorithm, that low-cost algorithm. But the difference is that, again, those non-periodic jobs are considered lower priority, so they only use the residual capacity, whatever's left over after already allocating all of the mission-critical periodic jobs. Dynamic reprovisioning. The dynamic reprovisioning algorithm is Morpheus's way of dealing with the unknown. What should we do when a job is taking longer than expected? Morpheus does a good job of predicting how long a job should take, but occasionally there's unforeseen complications that could cause a job to take longer. That's why dynamic reprovisioning is in place so that Morpheus can handle that situation. Essentially what it does is it will dynamically stretch the amount of resources that are allocated to that job in order to try to speed up that task that's running too slowly. As you see in the graph here, this is the same job that's been run many times, yet they all didn't finish at exactly the same time. There is a window there, a range of times over which they completed, and what this graph is trying to indicate is that that window is the space in which dynamic reprovisioning could kick in and try to pull in some of those slow jobs so that they complete more quickly. Morpheus is primarily implemented as a set of extensions to Hadoop and Yarn. The automatic inference engine is implemented as a standalone service, so it's not directly run as part of Yarn or Hadoop, but it is continuously processing the data, and it will send requests to Yarn in order to ask it to provision resources, for example. And it does that via Yarn's REST endpoint. The reservation placement component, however, is actually implemented as in-process functionality within Yarn, within the resource manager. And this is the component that actually implements that low-cost algorithm. The dynamic reprovisioning component, however, that's implemented within the resource manager as a monitoring thread. And that's just constantly observing the jobs and seeing if there's any jobs that are running too slowly, and if so, it will trigger additional resources to accommodate that. There were two main engineering challenges that needed to be overcome in order to properly implement Morpheus. Those two challenges were scalability and cold starts. So as far as scalability goes, the Yarn resource manager was really only designed to handle a small number of queues, and those queues were not meant to be reconfigured constantly. Morpheus, though, it's constantly reconfiguring queues in order to match the provisioning skyline. So the authors had to rework Yarn's queue locking mechanism in order to make this work. This allowed for the many more queues to be deployed and for those queues to be reconfigured very often. Now this did require that the consistency requirements were relaxed, but the authors didn't see that as being a big problem in this particular use case. Now the other big problem was cold starts. Basically, how do we handle jobs that we haven't ever seen before? If we don't have any data to look at, or not enough data to determine what the real demand is for this job, how does Morpheus know what to do? And the authors suggested either using an existing fair queuing mode, just falling back to manual provisioning where the user would specify directly how to provision those jobs, or possibly doing something specific to the particular application, where if you know the environment that the job's running on, that may give you some clues as to how to properly provision that task. In order to evaluate Morpheus's performance, Morpheus was tested in various ways. The first one was to test its job provisioning capabilities. To do this, Morpheus was tested against a 1-month-long trace of jobs that were running on a 50,000 node production cluster. And in this test, Morpheus was compared to the manual provisioning that was being done by users on that cluster in the past. So if we look at the graph, you can see that the dashed black line is representative of the ideal case, where every single task is perfectly provisioned. No tasks are under-provisioned or over-provisioned. The light gray line that represents the user-provisioned tasks, as you can see, there's a pretty big deviation there where there's many tasks that are being over-provisioned. Morpheus, which is represented by the other lines, is much closer to that ideal ratio where every single job is being properly provisioned. The deviation in the different Morpheus lines there is just different values of the tunable parameter alpha, and the particular value of 1% was found to have a 13 times reduction in the number of SLOs that are violated. So the authors found this to be a really good balance of that parameter, which created a really significant increase in how many tasks were being properly provisioned. The authors also wished to evaluate Morpheus from the perspective of cluster size. If Morpheus were able to meet all of its other objectives, but it required increasing the size of your cluster, that would probably not be acceptable for most people because that would mean increasing the cost of running the system. So the authors wanted to ensure that it at least didn't make the cluster larger, and they actually found that they were able to reduce the size of the cluster, thereby potentially reducing the cost of the required resources. The reason for this is that Morpheus is able to densely pack jobs using its knowledge of the SLOs, and because it's not over-provisioning like users were doing manually, is able to utilize the cluster resources more efficiently. As we can see in the graph, it was actually able to reduce the cluster size for anywhere from a little bit less than 20% to as much as 30% when compared to the user provisioning. Again, depending on the different tunings of this alpha parameter. So this could significantly actually decrease the cost of running the cluster while still meeting the demand of all of the required tasks. The authors wanted to evaluate the effect of Morpheus's static provisioning and its dynamic provisioning individually to see how they each affect the system. So tests were run with dynamic provisioning completely off and static provisioning completely on, and vice versa with only static provisioning on and dynamic provisioning off. The results of this are displayed on the graph on the side, and basically what we can see is that when Morpheus is running with only static provisioning, it essentially matches the number of SLO violations that were seen with manual user provisioning. This means that the number of tasks that are not meeting their deadline is essentially the same as before, but we were able to, in this case, reduce the cluster size by over 60%. So you could maintain the same performance that you have right now while reducing the cost by a very large amount. On the other hand, if you used only Morpheus's dynamic provisioning capabilities, you could retain the same cluster size that you have using manual provisioning, but you could reduce the number of SLO violations by 13 times. So you could have a dramatic performance improvement with the same cluster that you have now. Now, because Morpheus has tuning parameters, you can tune it to operate anywhere along that dashed line, depending upon your business needs, right? And you can decide what level of SLO violations you're willing to tolerate. The trade-off there being that if you want to reduce the number of violations, then you're going to have to increase the size of your cluster to accommodate that, which means additional cost. But the user is able to choose that, and they can potentially have the best of both worlds. Morpheus was also evaluated against a high-load production environment to ensure that it could run even under a very high load. So an 8-hour experiment was performed on a 2,700 node cluster. This cluster was running about 100,000 concurrent containers. As we're able to see in the graph, Morpheus was able to sustain this high load for the full 8 hours. It maintained a very high cluster utilization throughout the whole run. And it was able to remain responsive. So users were still able to submit reservations for ad hoc tasks, and those were typically met within 10 seconds, even though the system was still handling this very high load of periodic tasks. In conclusion, Morpheus was able to successfully attain most, if not all, of its goals. It was able to successfully derive SLOs by looking at the past history of jobs. It was able to enforce those SLOs for reoccurring periodic jobs by using efficient job packing algorithms that can utilize the slack time that SLOs naturally elucidate. It utilizes dynamic reprovisioning and uses that to reduce the unpredictable variance that may show up when jobs are running, to try to pull in slow jobs that were unexpectedly taking longer than predicted. It was able to handle production level load and scales well to very large cluster sizes with many containers and many simultaneous tasks. It could reduce SLO violations by between 5 to 13%, depending upon how you tune it. And it's able to reduce the cluster size by between 14 and 28%, again, depending upon how the system is tuned.